final interesting thing is the interface, okay. And this interface, if you look at it, there are a whole lot of signals out here. Let's try and understand them a little bit, because that becomes important to how you are finally going to implement this in hardware, right. Broadly, look at the first 6 signals, okay. Let's try and understand what they are. What it's saying is any module that is getting implemented has these signals. There is a clock, which is called AP_clock, which is an input. There is a reset and a start, those are also inputs. And the next one is the done, idle and ready are all outputs of this module. Of these, the AP done is basically a signal saying that, you know, I started at some point, when the computation is completed, AP done goes high. AP idle is a less useful signal. There are specific cases in which you might want to use it, but most of the time you can probably just ignore this one. And AP_ready, at the module level at least, you know the idea behind it. The principle is just that once you have given the start signal, it will not show ready again until it is ready to accept the new input. That might happen before done, right. So keep that in mind. The way that these signals work is, I give it a start signal. After some time, the ready signal will again become high, indicating that it is ready to accept new data, but the done signal might not have gone high, okay. Done will happen only when the actual computation is completed, that is at the latency, whereas ready will go high at the initiation interval, okay. So those are the sort of standard handshaking signals that are available pretty much for any module, okay. But then we see that there are a bunch of other interface signals basically for the data in and data out, okay. And let's take data in M real and data in M image, right. Those are the real and imaginary parts. What you will see is there is an address, a chip enable and a actual data, the Q data. So there is a in address, in chip enable and data, and in fact there is separate data for the real and imaginary parts, right. I will look just at the real, okay. So the real address, there are 5 values, it is a 5-bit value, okay. Why does that make sense? Because the input is essentially 32 different values. The chip enable is just something to activate, saying that, okay, you know, read from this, or rather let's just notice that the chip enable is actually the address and the chip enable are both outputs of this module, okay. So I need to correct that. Both of these are coming out. Why? Because they will get fed into the module that is actually storing data in. This will be some kind of a RAM, okay. So if I feed it this address and the chip enable, it can then give me back data, okay. This is the interface that comes by default when you create something. The good thing about it is, essentially what it is telling you is, as long as your data is stored in an array somewhere, this module, the FFT0 module, the FFT module will take care of generating the addresses so that it reads from the correct place. So even if you are not reading exactly in the correct order, that is from 0 up to 31, it does not matter, it can generate the addresses correctly, right. In practice, we might want to switch this around and say, I want a stream interface instead. I do not want to be giving out addresses for each data that I am going to read. I am going to assume that I am going to get consecutive values of data, okay. That simplifies my interface a little bit, because, well, this is basically 16 real and 16 imaginary. Why the streaming interface simplifies my implementation is that I do not need to decide which address to read from. I just say next, next, next and get the data. And the understanding is that the previous module, rather than being a generic RAM block, is just something that is a FIFO, basically says, okay, this is the next data, this is the next data, this is the next data, right. Once again ties in better with the KPN model, but this does not require the KPN model. It basically says I can read from anywhere, any way that I want. Okay. Similarly, on the other side, you have for the output all three: address, write enable, chip and or all four rather, address, chip enable, write enable and data are outputs. Right. So, once again a 5-bit out address, chip enable and write enable, right. Maybe not strictly speaking necessary, you do not need to have two such signals, but this is normally done for writing anyway. You have one thing to activate the memory and the other one to say I am writing into it. And finally, real and imaginary 16 bits each. Okay. This is the interface that we have come up with. Okay. So, if you had some mechanism by which you can actually directly store your input in a block RAM, right, and then give the appropriate start signals to this FFT module, it will take care of generating the addresses to read in the data correctly, do all the computation and generate addresses that you can then feed into an out data module and actually store the data out there. Okay. So, this could be done without having any additional support circuitry, if I just wanted to use this as a standalone module. Okay. But in practice, what I am very likely going to be doing is, my FFT is probably not something that I just want to do standalone. I actually am going to use it as part of a larger computation, okay, which means that what I will actually have is some kind of a large C program or C++ program, and somewhere in it I will have an FFT function call, then a lot more until the end. Okay. Where is this going to run? It is basically going to run on a CPU which has associated with it some memory, right. The way that a laptop or any other computer works is there is a CPU, there is memory, the program that you want to execute is stored in that memory and is fetched one instruction at a time, and the data on which you want to compute is also stored in the memory and is fetched as and when the program tells you to load data from the memory. Okay. What I would like to do is to expand this functionality, have the ability to have a separate piece of hardware and say, can you get data either from the memory or directly written in from the CPU, do some computation and give the results back to the CPU so that it can write it into memory or directly write it back into memory, right. And the way that this is done in practice is that we build up a system that has all of these capabilities, and in order to take care of the talking between modules, right, I have something that we call a bus, and this bus allows me to have my accelerator module attached to it in such a way that when certain instructions are seen by the CPU, they will automatically send information to the accelerator, which will perform whatever work it is supposed to do and give me back results. Okay. How do we build something of this sort? What we have seen over here is we have completed the synthesis. What we can do is, there are two further steps that I am not going to go over right now in class, but you can go through it. The first thing you would have seen, of course, is that the C simulation works because the test bench works. Once you have completed the C simulation, you can also run a so called RTL co-simulation, which will allow you to run the entire hardware that was generated, which supposedly takes 511 clock cycles to compute an FFT and so on, and you can actually see the hardware signals corresponding to that. After all that is done, you can then go through the process of exporting this RTL. Okay. Now, export RTL, essentially what it does is, the synthesis that you ran has generated some Verilog code, and it is going to export it in a manner that can then be used by some other module. In this case specifically, a processor plus memory system like this. We want to be able to write it out in a way that I can actually attach it as an accelerator onto a larger system. Okay. How do I create such a accelerator? That is done in the other tool, not Vivado_HLS, but Vivado itself, right, which allows you to create a block diagram which involves a processor, some supporting structures such as the memory, your peripherals, and it automates a lot of the processes such as actually creating that bus and connecting things to it.